Hello, this is Terry again. A couple of videos ago, I showed you how to derive the sine and cosine series. And today I'm going to show you how to derive the sine and cosine function in product representation. And this is a very much a step-by-step approach to how you do that. All right, series representation of the sine and cosine functions, of course, are well known. It's used often in a lot of practical work. But in many applications, the product representation, in other words, not representing as a series, but representing as an infinite product, is actually more useful. Here we're going to provide you a detailed derivation of how you get the product representation of sine and cosine function. There are different approaches. See this reference here, for example. But so what we want to do today is we want to start with the sine and cosine function defined on a complex plane, and then we'll use the Tanner's product limit swap theorem that I did in the last video to help us figure out a very important step in deriving the product version. All right, so let's start with the sine and cosine function defined on a complex plane. Now, in one of the previous videos, I think 2 videos ago, I showed you how to start with a triangle using calculus and differential equations. You can derive the sine and cosine series given here. Now, if you take any real argument theta, remember the argument for these series are real, right? You can do the complex version, but all you really need, I think, is sine and cosine, the real version. So if you take theta, it being real, right? Then if you plug in into the cosine series, like you're going to get cosine theta, and then if you plug in the sine series, and then for each term here, the result here, you multiply that by I, and then you add the two together. Well, you're gonna clearly see that it has a form of e to the I theta, where I is square root of minus 1. Using the properties of I, you can clearly see that. And then similarly, sine being a odd function, if you do a sine minus theta, and you're gonna get e to the minus I theta. This is Domof's theorem. I also did a video some weeks back, on that, so feel free to take a look at that. All right, so what happens if you take these two equations and add them together? Okay, so for example, e to the I theta plus e to the minus I theta, you're gonna get 2 cosine theta. Similarly, if you subtract the second equation from the first, e to the I theta minus e to the minus I theta, you're going to get 2I sine theta. So why is this important? Because looking at this form, we can now use it as an analogy and say, hey, you know what? We can replace the real theta with a complex z. So sine z is defined as e to the iz minus e to the minus iz all over 2i. And cosine of z is defined as e to the iz plus e to the minus iz over 2. So now if you define sine z and cosine z like this, then you can build up the product representation. That's the point of this video today. All right. To do that, to get to the final form, we're going to need to go through a number of steps. This is involve a little bit of algebraic work here. So I'm going to show you step by step how to actually do that. All right, let's start with unit roots. Here's lemma 1. Let's just quickly recall, right? For every natural number k, if you try to solve the equation u to the k minus 1 equal to 0, right, you're going to get these roots, right? These are the unit roots because essentially u is a complex number, of course. Now let's prove that quickly. Remember, you can put complex number in its polar form, right? So u is any arbitrary complex number, any complex number. We want to find out what complex number will satisfy this equation. Those are the roots. So if you let u equal to r e to the I theta, remember r is the radius, the distance between the origin to the complex number, because remember every complex number on the complex plane is a point on the real imaginary plane, right? So if a complex number u is r e to the I theta, then u to the k is going to be r to the k e to the I k theta, right? So the roots of u to the k minus 1 equals 0 is obviously just a solution of u to the k equal to 1. Now here's a trick. 1 is a real number, but every real number is also a complex number, right? So what happens when you represent 1 as a complex number? especially in polar form? Well, it's going to get e to the minus 2 pi j. Now, remember, you can do e to the plus 2 pi j, but here it's actually better off to do e to the minus 2 pi j for our purpose. So e to the minus 2 pi j, you can run as many as you like, but it turns out we only need the first k of them, right? So j equals 0 up to k minus 1. The reason is because of the fundamental theorem of algebra. Right, this u to the k minus 1 is a kth polynomial, so it only has k roots. So we don't need to go beyond that, because beyond that is going to repeat on the complex plane. So all you need is just j equals 0 to up to k minus 1, the first k of them. Okay, so if I plug everything in, this r to the k, e to the u to the k equal to 1 is the same as r to the k, e to the ik theta equals to e to the minus I 2 pi j. Remember, j runs through this. Well, by looking at this form, you can clearly see r must be 1, right? Of course, because this is a unit, right? So r must be 1. And then what about the rest of them? So if you distribute it around the unit circle, we need to go through all the locations of where this is true. Well, all you have to do is set ik, remember k is given, right? Ik theta equals to minus I 2 pi j. I and I cancel, that means k theta equal to minus 2 pi j. So solving for theta, and now it's indexed by j because there are k of them, is going to be minus 2 pi j over k. Again, j runs from 0 up to k minus 1. So what does that mean? That means there are k arguments that will satisfy this equation. The first one, when j is equal to 0, obviously, the first one is 0. When j is equal to 1, it's going to be minus 2 pi over k. When j is equal to 2, it's minus 2 times 2 or 4 pi over k, etc. Until the last one, the kth one, kth argument is going to be 2 times k minus 1 quantity times pi over k. Okay? So if these are my argument, now bring it back to this form. Remember, I'm trying to solve for u always has the polar form re to the I theta, but r is 1, and theta is these theta sub j, so it's basically u equal to e to the theta j, right? So plugging in u sub 0, the first argument is going to be 1, because e to the 0 is 1, and then u sub 1 is going to be e to the minus 2 pi over k times I. And then the second one will be e to the minus 4 pi over k times I, etc. Until the last root is going to be e to the minus 2 times k minus 1 quantity pi over k times I. And those are your k roots. And now we're going to use this in the next step to help us prove another part. All right, let's go to the second one. Now, again, for the lack of a name, I just made one up. I just call it factoring the exponential identity. But what's important is not the name, right? What's important is this little piece here. It's that for all complex numbers z, right, and any natural number k, e to the ikz minus e to the minus ikz, you can factor it like this into a product of k factors. Each factor, I factor is e to the zi minus e to the minus z plus 2j pi over k all times I. Now, in a minute, you will see, at this point, you'll look at it and say, what is so important about this? In a minute, you will see why it will help us solve an important problem as part of the proof. So quickly, here's the proof. If you let u equal to 2zi, right, then again, using what we have just learned in the previous slide, these are the roots, okay? So, all right, so what do we get? So e to the ikz minus e to the minus ikz. First, I'm going to pull out e to the minus ikz. Right? So if I do that, then to compensate this, I'm going to need to make this the first term e to I 2kz, right? Because this times this gives you back the first term. And then, of course, the second term is minus 1. Okay. But now, think of e to the 2zi as u. So this is just e to the minus ikz times u to the k minus 1. What are the roots? By the previous lemma, these are the roots. Right? You factor them out like this. Okay. Now, substitute u equal to e to 2zi, right? Plug it back in. So you're going to get these, right? And then now remember, all of these, starting except the first factor here, at the e to the minus ikz, the rest of these factors, k of them, can be written in product form. That each is going to be e to the 2zi, so notice this has nothing to do with j, minus e to the minus 2 pi j over k times I. Remember, in this case, I is always square root of minus 1, right? It's an imaginary number. All right, so equal to this. Now, here's a trick. This is important, and we're going to see how to use this trick again. You see this e to the minus ikz. Think of this as e to the minus iz being raised to the kth power, right? So when something a is raised to the kth power, you can actually squeeze it inside the product. It's just a. Because think about it. If this e to the minus iz is inside this product like this, right? what is happening is this is a constant, right? This has nothing to do with j. E to the minus zi has nothing to do with j. So if you put it in the product, multiply k minus 1 time, all you have is just e to the minus ikz. So this is equivalent. But by taking e to the minus ikz, squeezing into the product, you're going to get something like this, right? So if you haven't done a lot of product work, this is basically how it happens. All right, so now take e to the minus ic, distribute it inside e to the 2zi. You're going to get e to the zi minus e to the minus the quantity z plus 2j pi over k all times I. Okay? So this is a very nice little identity, but we are going to be using this in the next few steps. All right, next, I'm going to talk about this, what I call, again, for the lack of a better name, I just call it multiple angle sine. So basically, it goes like this. For all complex z, again, and for every natural number k, sine of sine kz basically is multiple angle, right? I can factor it out like this. Into 2 to the k minus 1 times the product of sine of z plus j pi over k, where j runs from 0 to k minus 1. So let's see how we can do that. And again, this is going to be important. So by definition of sine of z, remember sine of z is e to the iz, right, minus e to the minus iz over 2i. So if I replace z with kz, then I'm going to get e sine kz must be e to the ikz minus e to the minus ikz all over 2i. Right? So if I multiply 2i on both sides, I'm going to get 2i sine kz is e to the ikz minus e to the minus ikz. But by the previous lemma, right, by the previous lemma here, we know this e to the ikz minus e to the minus ikz can be factored like this. So here we go. So I'm going to factor it. Let's call it expression 1. But now observe something. Let's take a look at inside this product, right? For each fixed j, right, from 1 from 0 to k minus 1. Let's write this out a bit. E to the zi minus e to the minus z plus 2j pi over k all times I. I can factor one copy of them out, e to the minus j pi over k I. If I do that, of course, to make it back to e to the zi, I need to multiply, right? Because I'm taking a negative out, so I better add something back in, right? So to compensate. So that's how you get the first term. But now the second term, even though you see inside this negative, I got 2 copies. Since I factor 1 out, all I have now is just 1 copy left. So you're going to get this, right? But what's this? This parentheses, right? Again, by the definition of sine in complex form is 2i times sine of z plus j pi over k. You see that? E to something positive I minus e to the minus that same thing I. So that's sine z plus j pi over k times 2i, and then times this factor. So in other words, I can now write this expression 1 as 2. Okay, by the way, so you see this 2i on this side, right? I'm now going to move it back to the right hand side. So I'm now going to get sine of kz. I'm isolating sine of kz. So this is going to be 2i all raised to the minus 1 times the product, right? But instead of writing this, I'm going to replace it with this. This is going to be 2i e to the minus j pi over k times I times the sine of z plus j pi over k. Okay, now once again, you see this 2i here, right? This is a constant. When a constant is inside a product, you can pull them outside by just raising it to the k, right? Because here there's k minus 1 multiplication. So this becomes 2i raised to the kth power. And similarly, this e, so e to the minus j pi over k times I. Now remember, we're indexing through j. So remember e to the a, right, times e to the b is e to the a plus b. So if I were to pull this e to the minus j pi over ki outside, how do you resolve the j? Well, it becomes a sum. So this is just e to the minus pi over ki times the sum of j. J runs from 0 to k minus 1, right? That's how you pull constant out of product. All right, so now the rest is just the same, right? The product of sine of z plus j pi over k, where j runs from 0 to pi to k minus 1. All right, now we're going to wrap it up by making one more observation. So you see this guy here, this e to the minus pi over ki times this sum. How are we going to resolve that? Well, that's actually turns out to be something very easy. E to the minus pi over ki times this sum. Let's replace the sum. You know how to add up the first, you know how to add up sum j runs from 0 to k minus 1. It's k minus 1 times k over 2. Right? So you notice this k over here, right? This k and this k will cancel. And then the rest is just going to be e to the minus pi over 2 times I, all raised to the k minus 1. But on the complex plane, remember, this is polar form. What is e to the minus pi over 2, right? Remember, e to the positive argument is counterclockwise. E to a negative argument is clockwise. So if you think about starting at 1, 0, right? The coordinate 1, 0, or just 1 in the real 1, how do you move pi over 2 clockwise? You're going to end up to minus I. Remember, because on the complex plane, the horizontal axis is real, the vertical axis is imaginary. So this is just nothing but minus I, all raised to the k minus 1. But what's minus I? Minus I, if you multiply top and bottom by I, you realize it's going to be just 1 over I. So in other words, all these things just add up to 1 over I, all raised to the k minus 1. So all of this on the left-hand side, okay? Seemingly complicated stuff really just sum to, or simplifies to 1 over I, all raised to the k minus 1. So why is that important? Well, because I can now replace this in here. So going back to this, right? So replace this whole thing by 1 over I raised to the k minus 1. It's going to cancel with some stuff, right? So this is, so this here, 2i all raised to the minus 1 times 2i all raised to the k is 2i raised to the k minus 1. I can pull the 2 out separately, 2 to the k minus 1, I to the k minus 1, right? So when I do 2 to the k minus 1, I to the k minus 1, and then multiply by this guy, which is 1 over I all raised to the k minus 1, you can clearly see this and this cancel. This thing goes to 1. So all you have left is just 2 to the k minus 1 times the product of sine of z plus j pi over k, where j runs from 0 to k minus 1. And that's the end of this proof. Now again, this multiple angle is all going to come. What we're doing now is I'm building this up step by step with all these tiny little factoids, right? Eventually, I'm going to bring them all together in proving the big theorem, which is how to establish the infinite product of sine. All right, one more. This is what I call the sine reflection identity. Again, don't worry about the name. It looks like a reflection to me. I just made up a name. Again, yeah, for the lack of a name, I just call it something. That's not important. What's important is the following. You take any two complex numbers, z and w, right? Sine of z plus w times the sine of z minus w simplifies to sine square of z minus sine square of w. Okay, so again, very simple proof. This is literally just a one-page proof. So sine of z plus w, sine of z minus w. What do you do? Well, just use the definition. Remember, sine of w is e to the w minus e to the minus I w over 2, right? So plug it in. So every time you see that, just plug in z plus w. So e to the iz, e to the iw, minus e to the minus iz, e to the minus iw, all over 2i. And then this is the same thing, z minus w. You just get a negative. You just flip the sign. But everything else is exactly the same. So now there are 4 terms, right? A, B, C, D. Multiply them. This times this is e to the iz, because the e to the iw and e to the minus iw cancel. So all you have is e to the iz. This times this becomes e to the minus e to the 2iw. This times this is minus e to the minus 2iw, and then this times this is plus e to the minus 2iz, and then all over 2i squared, 2i times 2i, right? Now, you see here, I'm going to break this up into 2 because they have the same common denominator, right? I'm going to break it up into 2 like this. But now watch what happens. I'm going to subtract the 2, and then here I'm going to subtract a 2. Now, you see this minus 2 times this minus sign become plus 2. So plus 2 and minus 2 add up to 0. So this is a classic trick of subtracting something and adding something, right? Why did they do that though? When I do it like this, watch what happens. I can write e to the 2iz as e to the iz squared. And then this minus 2, I'm going to write this minus 2 times e to the iz times e to the minus iz. You notice this is just 1, right? So is that, in other words, instead of saying 2 times 1, I'm going to write it as minus 2 e to the iz, e to the minus iz. And then this is e to the minus iz, so thing squared. Same thing over here, except it's now w instead. So why did they do that? Because this reminds you of something, right? This is like a squared minus 2ab plus b squared. So that's e to the iz minus e to the minus iz all over 2i squared. Because that's 2i down at 2i times 2i at the bottom, right? So this becomes what? Exact same thing, except instead of z, it's w. Same thing. So hey, but that's sine square of z by definition. Remember, e to something minus e to minus something divided by 2i. That is sine square of z. So this is sine square of w. So it's sine square minus sine square of z minus sine square of w. Okay? So that proves that. All right. Let's see the next term. Yeah, so this is the last one. So this is the last little fact that we're going to need, and then we can then dive into building our major theorem. Lemma 5. For all natural number m, okay, what happens if you take the product of sine of j pi over m, where j runs from 1, not from 0, from 1 to m minus 1. Remember, if j is 0, sine j pi over m is going to be 0, so you're going to wipe the whole product out. So no, we're not doing it from 0, we're doing it from 1 to m minus 1. This is important, okay? What happens when you look at this product for any natural number m? Well, it turns out that's just m over 2 to the m minus 1. It simplifies it to some very nice number. And let's prove that. Remember, all these j pi over m, right? What happened is to prove that I can pick any z, any complex z, with the exception that it cannot be a integer multiple of pi. So no integer multiple of pi. So you can pick any z you like, but no multiple integer of pi. So as long as you stay away from these numbers, okay, then by the result lemma 3, right? Remember lemma 3 over here. Lemma 3 says you can factor this guy out, right? So sine of mz over sine of z, this ratio is going to be 2 to the m minus 1, right? So here's the reason why. So let's go back to lemma 3. Oops, let's go back to lemma 3. You see lemma 3? Lemma 3 starts from j equal to 0, right? But we cannot have j equal to 0. So we need to start with just product from j equal to 1. So what happened when j is 0? Well, 0 times pi is 0. So this is the sine z. So in other words, I can turn this by pulling a sine z outside and make it a product from j equal to 1 to k minus 1, right? So now when you do that, and you plug it in here, that's exactly what happened. So because once I pull out a sine z, I can divide both sides by sine z. Again, remember, I'm staying away from those integer multiples of pi. So I'm not going to ever need to worry about dividing by 0. So I can pull the sine z out, and this becomes a product of j running from 1 to k minus 1 of this guy. Okay? So by dividing both sides by sine z, I'm going to get 2 to the m minus 1 times a product of sine of z plus j pi over m, where j runs from 1 to m minus 1. Okay, now make a change of variable. Let's call z prime equal to mz in the numerator. Then what happens? Mz on the left hand side in the numerator, if I let z prime equal to mz, you agree, right? As z goes to 0, ultimately what I want to do is I want to see what happens when z goes to 0. Because to prove this, I need z to go to 0, right? So when z goes to 0 on the left hand side, right, you agree z prime also goes to 0, right? Because m is fixed. M is a fixed natural number. So z goes to 0 implies z prime goes to 0. Okay, so now let's put it in here. So limit z goes to 0 of sine mz over sine z. Well, remember, we're only looking at the left-hand side of only this side. Forget about this for a moment. Just look at this. So this is limit of z goes to 0. Now, this is a classic trick. As long as you stay away from 0, right, you can divide top and bottom by mz. So this becomes sine mz over mz on the top, and the bottom is sine z over mz. Now, 1 over the reciprocal m, I can just take it up to m like this. So m times limit as z goes to 0 now breaks into two limits. At the top is z prime goes to 0. And I'm going to call this sine z prime over z prime. The bottom is just regular z. Z goes to 0, sine z over z. We all know by now, right? This limit is well known to be 1 at the top. This limit is well known to be 1 when z goes to 0. So this is just m times 1 over 1, or m. So the left-hand side is just m when z goes to 0. Okay? What about the right-hand side? Well, so let's work backwards. So now m equals to this limit, but a limit of sine mz over sine z. But sine mz over sine z equals to this. So this is the same as 2 to the m minus 1 times the limit as z goes to 0 of this product, sine of z plus j pi over m. Now, if you learn, if you take limits in complex analysis, one of the lessons you learn in taking limit is limit of the product is equal to the product of the limit, so long as the product is finite. Remember, when the product is finite, you don't have to worry. You can always pass the limit in. The only run into problem is when the product is infinite. Remember in the previous video, I did the two Terrence theorem, right? One of which we're going to be using today, right? It clearly, I talked about that. You need to be careful. If it's finite product, you can pass it in, not a problem. But if it's an infinite product, you need to be careful. Here in this is the case where I only have finite product. So I don't need to worry about it, right? So I can just pass a limit through. So what happens when you pass a limit through? Limit of the product, finite product, or equals to the finite product of the limit. And now you're taking just the limit of sine of z plus j pi over m. But sine is a continuous function, and the limit of a continuous function you can pass into the argument. This is now just when c equal to 0 is just sine j pi over m. So the product of sine j pi over m, where j runs from 1 to m minus 1, times 2 to the m minus 1 is just this. So it's just m over 2 to the m minus 1. So if you divide 2 to the m minus 1 on both sides, okay, like this. So m equal to 2 to the m minus 1 times this product. So this product is just m over 2 to the m minus 1. That's how you prove it. Okay, I have all the little facts that I need, right? We are now going to prove the big theorem, the main theorem, which is how do you write the sine, how do you define the sine of z, right, as a infinite product? So here's a theorem, the main theorem. For all complex number z, sine of z can be written as z times the infinite product. So again, this is be very, very careful. This is now the infinite product of 1 minus z squared over j squared pi squared. Okay, so this is going to involve a number of steps, right? It's gonna go through a few slides. So let's do this. All right, starting with, for all complex number zeta, right? It is well known sine of zeta minus pi is minus sine zeta. Right? You can use either I theta definition to prove this. It's very straightforward. Sine of zeta minus pi is equal to minus sine of zeta. Well, what does that mean? That means for all complex w, right? So if I let w equal to, if I let zeta equal to w plus j pi over k, then this becomes just minus. So sine of w plus j pi over k minus pi, zeta minus pi, right, is equal to minus sine of zeta, or minus sine of w plus j pi over k. Okay, so for each fixed k, remember, by lemma 3, right, sine of kw equals to this. It factors out like this. Now, here's a key. To understand this, right, remember, this is valid for any natural number. So certainly it's going to be valid for an odd natural number. So let's consider an odd natural number. So in other words, let's take k equal to 2n plus 1, where n runs from 0, 1, 2, 3, and so on. Then using the result lemma 4, as well as sine of zeta. Okay, remember this, right? Sine of zeta minus pi is minus sine of zeta. So if I multiply negative 1 on both sides, then negative sine of zeta minus pi must be positive sine zeta. Okay, using these two factoid. Now watch what happens. Sine of 2n plus 1 times w is equal to what? 2 to the 2n plus 1 minus 1, right? Then times the product. J, remember, it's 2n plus 1 minus 1 up to this. So it's the product from j equal to 0 to 2n. Sine of w plus j pi over 2n plus 1. Remember, this is m minus 1. So if m is 2n plus 1, m minus 1 is 2n. So this is the product that runs from j equals 0 to all the way to 2n. Remember that. Now, watch what happens. This 2 to the 2n plus 1 minus 1 obviously is 2 to the 2n. But this sign, it goes from 0 to 2n. I'm going to break it up into 2. I'm going to first let it run from 0 to n, and then I'm going to let it run from n plus 1 to 2n. Okay? When it runs from 0 to n, I'm just going to keep it like this. Sine of w plus j pi over 2n plus 1. However, remember this. Minus sine of zeta minus pi is sine of zeta. I can always write, instead of writing sine of zeta, I can write them like minus sine of zeta minus pi. So in the second part, from n plus 1 to 2n, instead of writing sine of w plus j pi over 2n plus 1, I'm going to write it as a negative sine of w plus j pi over 2n plus 1 minus pi. Right? So zeta minus pi. Minus sine of zeta minus pi is the same as sine of zeta. Right? All right. You see this product times product, right? It's the same as one big product. So you see this minus 1 here. Remember, this minus sign, think of it as minus 1 times something, right? Remember, every time there's a constant, if you want to pull it outside the product, okay, it's the same as minus 1 raised to that thing. How many do we run here? A1 goes from n plus 1 to 2n, so there's n copy. So this must be 2 to the 2n times minus 1 to the n. Okay? And then the first part is going to stay the same. The second part is just going to do this without the negative sign. Now, j pi over 2n plus 1 minus pi, I'm going to simplify a little bit and make it like so. This is algebra, right? But now watch what happens. Imagine when j is equal to 2n. So let's focus on the second product. What happens when j is 2n? 2n minus 2n is 0. So this becomes minus 1. So in other words, when j is 2n, this corresponds to minus 1. When j is 2n minus 1, this corresponds to minus 2. And so on. When it goes all the way back down to j equal to n plus 1, you're going to get n plus 1 minus 2n minus 1 is just minus n. So in other words, these things just run like this. So then you realize that, hey, wait a minute. Since this is product times product, I can squeeze in the same product, right? But hold on a minute. It seems like we don't need two indices, right? We don't need to break it up into two groups because looks like just one single thing, except instead of running from j equal to 1 to n, it's going to run from j equal to minus n to n. Because from negative n all the way up to negative 1 is just this guy. And then from 0 to n is just this guy. So this is the same as the product from j equal to minus n to n. Excuse me. Pause the video and take a look at this, if to make sure you convince yourself that this is correct. But this is the same product, okay? So this is one of those just, change of index, if you like. So that's what it is, right? It's going to end up like this. All right, now, then you do it one more step, and now you try to unwind it again. Now, remember, this guy here is symmetric, nice, but except 0, right? When j is equal to 0, it doesn't play, it doesn't really, have a correspondence to a negative 0, right? So I can't quite split them because ultimately I want to split them like this, but I can't do that with j equals 0. Okay, what happens when j equals 0? This is just sine of w, right? So pull them outside. So in other words, let's just treat sine of w separately. So this is 2 to the 2n minus 1 to the n sine of w, and then all I have now is minus n to minus 1 and then 1 to n, right? So what happens when I claim you can just write like this, because what happened? Look what happened when j is equal to 1. When j is equal to 1, this guy runs the positive 1. But at the same time, he also runs a negative 1. Because when j is 1, this is just negative j. So that covers up j equal to minus 1. So in other words, I can consider j as a pair. I can consider j equal to plus 1 minus 1. J equal to plus 2 minus 2 simultaneously. Right? So this becomes just the product running from j equal to 1 to n of sine of w plus j pi over 2n plus 1 times the sine of w minus j pi over 2n plus 1. But now, wait a minute, look at the reflection thing, right? This is sine of w plus something times sine of w minus the same thing. But remember, so that's sine squared of w, right? Minus sine squared of this thing. Remember, that's the reflection. That's lemma, was it lemma 4? No, yeah, this guy, right? That's just this guy right here. So sine of z plus something times sine of z minus the same thing is sine square of z minus sine square of w, right? So that's what we ended up. We're going to end up with this sine square of w times minus sine square of j pi over 2n plus 1. Okay, continue. So now I'm going to push the minus 1 back in. Remember, I have this minus 1 to the n outside. Now, but by now you should remember, right? So every time you have minus 1 to the n, if you can push it into the sign, into this product, put it into this product, it's just minus 1. So what happens if you do a minus 1 of this guy? All you do is just switch the order, right? Instead of sine square of w minus this guy, is this guy minus sine square of w, right? So you just flip them around. Okay, but what about, all right, so now I'm going to have this. But over here at this point, I'm going to factor j pi, sine square of j pi over 2n plus 1 out. So I'm just looking at inside this square bracket, okay? I'm going to factor it out. Now, at this point, when you factor it out, the first term becomes as 1. The second term becomes sine square over w over this. Now, you might say at this point, wait a minute, you're dividing by sine square, right? Will I ever divide by 0? The answer is no. So here's the reason why, right? So you see this j runs from 1 to n. So so this one from 1 to n, anytime you take a number from 1 to n, right, and you divide by 2n plus 1, that's not going to be a whole integer. That's not going to be an integer. That's not going to be a natural number at all. So you're not going to be a natural number times pi. So in other words, this will not be 0. So this is perfectly legitimate. Okay? All right, so you're going to end up with this. Now continue. So this now, so I'm going to break this one product into 2. So first product is going to be sine, just sine square of j pi over 2n plus 1, just this guy, running from j equal to 1 to n. Then this guy, the second one in the square bracket, I'm going to run them from j to 1 to n. All right, let's just call it star right now. Okay, let's call this expression star, and then we're going to continue. But before we continue, we need to observe one more thing. So again, I want to deal with this first product here. Now you see, remember sine of w, remember that sine of w, right, is minus sine of w minus pi, remember that? Right? But sine is an odd function. So negative sine is sine of negative. So it's negative sine of an argument is a sine of a negative argument. So I can push this minus 1 inside the sign, and instead of w minus pi, it's going to be pi minus w. So you agree, this is true for all w. Okay, so now, That means, let's look at this. What's sine square of j pi over 2n plus 1? Sine square of j pi over 2n plus 1 is, remember this is square, so I got two copies. The first copy, so it's sine times sine, right? So the first copy, I just call it sine of j pi over 2n plus 1. Let's call it that. But the second one, instead of calling it sine of j pi over 2n plus 1, I'm going to call it sine of pi minus j pi over 2n plus 1. From this, sine of w equal to sine of pi minus w. So the second copy, I'm going to make sure I'm going to call it like this. All right, so again, simplify this 2n plus 1 minus j all times pi over 2n plus 1. Right? This is just simplifying the argument inside. So now I can write sine square of j pi over 2n plus 1 as a product of these two signs. All right, so what does that mean? That means the product of sine square is going to be the same as so think about it this way, right? So when you're multiplying, so let's run through this. What happens when j equals to n? When j is equal to n, right, I'm going to get 2n plus 1. Look at the second factor, 2n plus 1 minus n, which is n plus 1. So in other words, when j is equal to n, this corresponds to n plus 1. When j is equal to n minus 1, it's going to be 2n plus 1 minus n plus 1 is going to correspond to 2. Right? And so on. So in other words, these two arguments, the index runs in parallel. Right? But what happens now is, because you have two copies, right? So you can re-index it by running it instead of, because remember it's two copies. So instead of running from 1 to n, you can first run it from 1, right? First run this from 1 to n, and then run this from n plus 1 to 2n. So together, I can take two factors into a single factor, re-index it to sine of m pi over 2n plus 1. So change the j to m. So and then run from 1m equal to 1 to 2n. From m equal to 1 to n, you're just running the first copy. From m plus 1 to 2n, you're running the second copy. So this over here can be written as this. Again, pause the video and think through this, right? But this is correct. All right. So what happens? But we know by lemma 5, we know how to simplify this. Remember, every time you take the product m equal to 1 to something of sine of m pi over 2n plus 1, right? It's just 2 to the n plus 1 over 2 to the 2n, right? So again, so this first product turns out to just simplify to something very simple. It's just 2n plus 1 over 2 to the 2n. So again, pause the video, go back, take a look if you like, but that's what happens. Okay. So now continue. So this guy here, the first product is now easy. I know it's just 2n plus 1 over 2 to the 2n, right? 2n plus 1 over 2 to the 2n. But 2 to the 2n and 2 to the 2n cancels. So all I have left is just 2n plus 1 times the sine of w times the second product. Okay? Now for the second product. All right. So look what happened. So suppose I let w, so you see this w, right? Instead of calling w, I'm going to do another transformation. Suppose I'm going to let w equal to z over 2n plus 1 for another complex z. But now remember, let's take z to be non-zero. Then this becomes what? Sine of z, right? So go back here, right? This guy, w, sine of 2n plus 1 times w. If w is z over 2n plus 1, this 2n plus 1 and the z over 2n plus 1 they cancel. All you have is a sine of z. So this side is a sine of z. Then it's going to be 2n plus 1 times the sine of z over 2n plus 1. Remember, everything where you see w, replace it with z over 2n plus 1 times the product of this guy, right? Everywhere you see w, replace with z over 2n plus 1. Now, this sine of z over 2n plus 1, right? I'm going to do a classic trick. Remember, because I'm taking z non-zero, I'm going to multiply by z, divide by z. Classic trick. And this 2n plus 1 is 1 over 2n plus 1. So in other words, this guy over here becomes the sine of z over 2n plus 1, all divided by z over 2n plus 1 times the extra z. All this, an outside the product equals to this, all this outside the product. And then the product is exactly the same. Okay? Now, you kind of begin to see where I'm going with this. This is going to be sine of something over something that goes to 0, right? That's exactly right. So ultimately, I'm going to be doing exactly that. But just hold that thought right now. All right, so this is where I need to begin to start thinking about how to pass a limit problem. Remember, eventually we're going to be dealing with infinite product. So we need to know how to pass limit through. So remember, as I said before, today in this video, as well as in my last video when I talk about the true ternary limit swap theorem, you got to be very careful when you're dealing with infinite product. If it's finite product, you have a lot less problem to worry about. But when it's infinite product, the limit of the product, infinite product, can you pass a limit in so that it will be infinite product of the limit? This is questionable, right? You need to make sure certain conditions are whole before you can say that. So what are those three conditions? So again, if you haven't watched my previous video, feel free to watch it, and it will have a more detailed explanation. But here's just a quick recap. Okay, so this is called the ternary product limit swap theorem. I made up the name, by the way, because there were two. One was for the series and one for the product. So I just called it the product limit swap theorem. So here's how it goes: is that let A sub j comma n be a sequence of complex numbers indexed by both j greater than equal to 1 and n greater than equal to 1. If these three conditions are true, then I can swap the limit. The limit of the infinite product equals the infinite product of the limit. What are the three conditions? For each j greater than equal to 1, remember this is the double sequence, right? This is a sequence of two indices. So you have a j, you have an n. So if I fix j and treat just a sub j comma n as a sequence, right, indexed by n, what happens when n goes to infinity? It has a limit. So I'm guaranteeing that every fixed j, the other index, as a sequence, the limit has a limit, alpha. Let's call it alpha sub j. Second condition, there's a sequence of positive numbers m sub j such that when for all n greater than equal to 1, in absolute value a sub j comma n is less than or equal to 2/6 of m sub j. Don't worry about why this weird 2/6. I do the 2/6 simply because it will make my math a bit easier, right? So again, you can just have an m sub j is fine, but it's easier to do the math if you have 2/6 of m sub j. And the last condition is when I sum up all these m sub j, these are no ordinary positive sequence. When I sum them all up as an infinite series, it's finite. So if these three conditions hold, then this must be true, right? So the rest of the theorem is pretty much going to be showing these conditions are true, and then we'll draw the necessary conclusion. All right, so remember we stop here, right? So let's continue. Now, here's what we're going to do next. Remember, ultimately, I need to use this theorem. So I need this sequence. So let's start with defining the sequence. Remember, if you look at this form, right, you're going to get this product is 1 minus something. You see this guy over here, right? So I'm going to let that be my a sub. You see this guy here, it depends on two. Remember, z is fixed. So it depends on j as well as n. So it's j and n. Okay. So I'm going to let a sub j comma n to be sine square of z over 2n plus 1. And then over sine square of j pi over 2n plus 1. So you agree, right? This depends on both j and n. Now I'm going to rewrite this a bit. So a sub j comma n is this guy, right? I'm going to rewrite things a bit. You see the top here. Suppose I divide everything inside z to the 2n plus 1, right? What happens when you do that? Well, you need to compensate that. You can't just divide something out of the blue, right? So to do that, remember I'm putting everything inside the square. So if I divide this, I need to multiply that same thing. So this whole thing, when you square, becomes z squared over 2n plus 1 quantity square. So this is legit. I divide, I multiply. Right? So it's the same as I multiply by 1. Similarly, at the bottom, I'm going to do the same thing. I divide j pi over 2n plus 1, but because it's square effect, so I need to multiply by j square pi square over 2n plus 1 quantity square. But look at the top and bottom. They both have 1 over 2n plus 1 quantity square. Obviously, they cancel, right? So all you have left is z square over j square pi square, right? And then, of course, these two, right? The two squares of two sides. Okay, now make a change of variable. Let zeta equal to this argument, z over 2n plus 1 in the numerator. So in the numerator, we replace this stuff with zeta. In the denominator, we replace these guys with c, a different Greek letter, right? Because they're different argument, right? So one is zeta, one is c. But in both cases, you do notice something. When n goes to infinity, right, z is fixed. So look at this. Look at this one right here. Z is fixed. When n goes to infinity, this zeta goes to 0. Similarly, over here, same thing. J is fixed. For each fixed j, when n goes to infinity, c also goes to 0. So the limit of for each fixed j, the limit as n goes to infinity, a sub j comma n, is the same as z squared times the limit of zeta going to 0, right, of sine zeta over zeta whole thing squared. The bottom is limit of c goes to 0, sine c over c quantity squared. Well, we know this, right? We all know this is going to be 1 because you can pass a limit inside the parentheses, and that's 1 square. And then the bottom is pass a limit into the parentheses, that's 1 square, right? 1 square is 1, so 1 over 1 is 1. So this simplifies down to z squared over j squared pi squared. That's right. So for every fixed j, letting n goes to infinity is just this. So it's alpha sub j. Let's call it alpha sub j. Guess what? The first condition of the ternary product theorem hold. Remember, the first condition said you need to prove that this guy is the limit exists. It does. We just showed that. All right, now let's try to see if we can do the second condition. Second condition involves finding this real sequence, right? So that this thing is bounded. So I need to actually figure out what is m sub j that will make this work. Well, let's do this. All right. So next, consider the expansion of sine of w around w equal to 0. Okay? And only focus w between greater than 0 and less than pi over 2. So in other words, I'm not going to look at all w. I'm only focusing on this interval, w in this interval. W in this interval, sine of w expands out to be w minus w cubed over 6 plus w to the 5th over 120 minus dot dot dot. Now, you can do some simple algebra and show, right? I mean, this is pretty straightforward, actually, if you think about it, because you see these guys, remember, I'm not focusing, like everywhere, right? I'm just focusing on w in this interval. W, only focusing in this interval, these denominator, right? You talk about the factorial of some odd number. The next one, for example, right, is going to be 7 factorial, right? Right? So these things is going to drop very quickly. So you can easily see this is greater than w, greater than just the first two terms, w minus w cubed over 6, which I can factor w out to be w times 1 minus w squared over 6. So that means if I focus in w between 0 and pi over 2, right, then sine of w over w, remember I'm strictly greater than 0. Right? If I'm strictly greater than 0, I can divide w. Sine of w over w must be greater than 1 minus pi squared over 24. Right? Why is that? Because in other words, what would make this the absolute lowest bound is when you take w to the absolute upper bound. So when w is equal to pi over 2, it's just gonna, when you plug it in here, it's just gonna be 1 minus. See, you see this sine w divided by w, right? It's be greater than 1 minus w squared over 6. I want to make this the lowest bound. That means I'm going to take w as large as I need to. But the largest I ever need is pi squared over 2. So what happens when you put pi squared over 2 into this w? You're going to get pi squared over 4 divided by 6. So that's pi squared over 24. So this, in other words, is greater than 1 minus pi squared over 24. If you evaluate this is greater than a half. Right? So in other words, I can now say sine of w over w is greater than a half, as long as w stay in this interval. Okay, so now let w equal to j pi over 2n plus 1, right? You can clearly see, w equal to j pi over 2n plus 1, right? You're going to satisfy this. Then sine of j pi over 2n plus 1 over j pi over 2n plus 1 must be bigger than a half, right? So remember, as j is fixed, as n gets larger and larger, right? Each j, it is going to stay inside this interval. So all of this is going to be greater than a half. So what does that mean? That means, remember, this 1 over the reciprocal of 2n plus 1 is the same as 2n plus 1 times the sine of j pi over 2n plus 1, and then multiply j pi across, you're going to get j pi over 2. So 2n plus 1 times sine of j pi over 2n plus 1 is greater than j pi over 2. If I take the reciprocal on both sides and square it, I'm going to get 1 over 2n plus 1 quantity squared times sine squared of j pi over 2n plus 1. It must be less than, remember when you take the reciprocal, you flip the sign, right? Less than 4 over j squared pi squared. Okay, so if I multiply 2n plus 1 squared across, I'm going to get 1 over sine squared of this, less than 4 times 2n plus 1 squared over j squared pi squared. Okay, now, so that's the first part, okay? Now, let's also look at the second part, because remember, ultimately, we need to do this part times 1 over this part. We have taken care of the 1 over. Now, let's focus on the second part. What happened when I take the sine of z over 2n plus 1? Whatever, remember, this z is complex, so sine produces a complex. So I can take its mod square. What happened? By the same expansion here, you can clearly see, because sine of w is w minus whatever, right? So it's less than or equal to W. So in other words, sine of W is going to be less than or equal to W. So this is the square version. It's just mod Z squared over 2n plus 1 quantity squared. All right, so let's call this double star. All right, so now let's bring everything together. Remember, ultimately, I need to prove this in absolute value is less than or equal to 2/6 of some m sub j, and we're going to figure out what it is. All right, remember, now go ahead and let a sub j comma n. I think I let the part to be positive. Doesn't really matter because you're taking absolute value. I think I might have let it be positive earlier, but it doesn't matter. It really doesn't matter. Let's take it positive because we're taking absolute value anyway. So anyway, absolute value, yes, make this positive if you like. So just so that we're consistent with the previous line. So when you take the absolute value, you're going to get absolute value at the top, sine square of z over 2n plus 1. Bottom is going to be absolute value sine square over j pi over 2n plus 1. But remember, by the first part here, the 1 over bit by double star, the numerator by double star is less than or equal to sine mod z squared over 2n plus 1 squared. The 1 over sine squared in mod by first star is less than 2 to 4 times 2n plus 1 squared over j squared pi squared. 2n plus 1 squared, 2n plus 1 squared, that cancels, right? What else? So this becomes just 4 mod z squared over j squared pi squared. So by looking at this, it is now clear what m sub j should be. I can just define m sub j as 6 over 2. Remember, I need 2/6, right? So I'm going to do 6 over 2 times this guy, 4 mod z squared over pi squared j squared. Remember, z is fixed, right? When we're doing this analysis, we're letting n go to infinity, we're summing j, z is fixed. So this above, by this, it must show that, if I let m sub j be this guy, then absolute value a sub j comma n must be less than or equal to 2/6 of m sub j. Okay? All right, so now the second condition of the ternary product limit swap theorem hold. So let's go back here. So now 2 conditions hold. I need the third condition to hold. Well, we have made a choice on m sub j. Well, let's show that it adds up to a finite number. Does it? Well, it does. So go back here, right? What happened when you sum up m sub j? Well, these are just a bunch of constant, right? So all these constant pull them outside. Remember, z is fixed. So z is actually a constant, right? So pull everything outside is 6 times 4 mod z squared over 2 pi squared. Pull them outside. Now all I have summing is just 1 over j squared. Now, this is well known to be pi squared over 6. This is a solution to the Basel problem. Again, I did a video a few weeks back explaining exactly how Euler solved this problem. So the sum of this is exactly equal to pi squared over 6. So not only do we know that it's finite, but we actually know the number. So we actually get more than what we need for in the ternary condition. So simplify this pi squared over 6 multiplied by these guys. It's just going to be pi squared and pi squared cancel, 6 and 6 cancel, 4 over 2 is 2. So this is just actually equal to exactly 2 mod z squared. So certainly it's finite, right? Okay. Well, because z is fixed, it's finite. The third condition of ternary product limit swap theorem is also satisfying. Okay. So what that means then is I can pass in limit now. When I take the infinite product limit, I'm now free to apply the theorem, pass in limit, because I have now demonstrated all 3 conditions of the ternary product limit swap theorem hold. All right, so let's see how we do that. All right, so let's continue. Remember, we have sine z equal to the limit n goes infinity of sine of this. I'm just continuing, right? Times sine z, remember, times z, times this product, right? Now, this first piece, let's leave it by itself. Z is a z, so let's leave it by itself. Now, I can limit as n goes infinity of this finite product. Finite product, but remember, this is n. This is n. So this is going to turn into an infinite product. That's how the finite product ended up in an infinite product, because of you're letting n goes infinity, right? So when you do that, this is 1. We have already shown that. So this is 1, this is z, so it's just z, right? So all we're dealing with is limit of this. Now remember, limit as n goes infinity of a partial product that runs from j to 1 to n. When you take that limit, right, this product becomes an infinite product. A finite product now becomes an infinite product. But you got to be careful here, because there's an n inside, there's an n in the index. So when you take the limit inside, remember that by the ternary swap, right, product limit swap theorem, I can pass a limit through. But when you pass a limit through, 2 things happen. First, the finite product becomes an infinite series. That you don't need the ternary theorem, right? Limit, you can always make this into infinite product. That's just a matter of definition. But now inside this limit, I need to be careful because that is not so clear. Because you'd have an n inside. So without the ternary theorem, you cannot go from this line to this line. Right? So you see that, right? Because you're taking a limit, going inside, you're passing into infinite product. So without the ternary theorem, I could not have done this. Right? It may not be legit. So now I know it's legit for sure. Okay, so I can pass the limit inside. So now I have this z times this infinite product of this limit. But now, same trick by now. You saw this before, right? I'm going to write sine square of z over 2n plus 1 as this guy, the numerator. We talked about this before. It's the same thing. You divide this and you multiply to compensate. The bottom, same thing. You divide this and you multiply to compensate. These two lines are equivalent. Okay? Now, the top, what happens when I let n go? Because remember, inside the square bracket, remember, don't worry about the product for now, right? I'm just inside this term by term for each fixed j. Limit as n goes to infinity, limit of 1 minus is 1 minus the limit, right? And then limit of the quotient, a over something over another thing, is limit of a quotient is quotient of limits. So this becomes 1 minus z squared. Remember, 2n plus 1 quantity square and 2n plus 1 quantity square cancel. All you have outside is just z squared on the top and j squared pi squared on the bottom, right? So this is z squared times the limit, right, of this guy. And then this is j squared pi squared times the limit of this guy. Now, for the numerator, for this part, let's define u equal to z over 2n plus 1. When fixing z, when n goes to infinity, it's the same as u going to 0. So this is limit of u goes to 0, sine u over u. The bottom, oh, I'm missing, there's a typo here. There should be a square here. So there should be a square here, okay? Yeah, I'm missing a typo. Yeah, so this is a square, this is a square. Yes, there should be a square. But it doesn't matter, it's gonna cancel anyway. But yeah, so there's a typo, guys. This should be a square here, this should be a square here, okay? So, now, the top is limit u goes to 0, that's 1. The bottom, if you let v to be j pi over 2n plus 1, again, holding j fixed, n goes to infinity, v goes to 0. So this is limit, v goes to 0, sine v over v. Again, there's a square here, okay? So, but this is 1. Doesn't matter, this is 1 square, that's just 1. So all of these are going to end up just 1 minus z squared over j squared pi squared. So sine of z is z times the infinite product of 1 minus z squared over j squared pi squared, where j runs from 1 to infinity. We have now completed the proof. We have now established the product representation of the sine function. And this is valid, right, on the complex plane for a complex argument. Okay? Let's just do a quick fun example. What is the infinite product of 9j squared minus 1 over 9j squared? Well, 9j squared minus 1 over 9j squared can be written as 1 minus 1 over 9j squared, which can be written as, again, classic trick, right? So 1/9 is 1 over 3 squared. But I'm going to multiply top by pi squared, and then multiply bottom by pi squared. So the top becomes pi over 3 quantity squared over the bottom j squared pi squared. So now you can clearly see the formula here, right? This is z squared over j squared pi squared. So by the above theorem, this whole product is the same as this product, which is just sine of pi over 3 divided by pi over 3. Okay? Remember, it's just sine z over z, right? Sine of pi over 3. Z in this case is pi over 3. So sine of pi over 3 over pi over 3. Sine of pi over 3 is square root of 3 over 2. So over pi over 3. So it's just 3 root 3 over 2 pi. Okay, so this infinite product evaluates this. Okay, so that's the sine. What about the cosine? Right? We established the infinite product for sine. What about the infinite product for cosine? Well, it turns out it's equal to this. It's cosine of z is infinite product for all complex z. Cosine of z is infinite product of 1 minus 4z squared over 2k minus 1 quantity squared pi squared. Like this. How do you prove something like this? Well, we call that for all complex z, sine the double angle form. You can use e to the I theta minus e to the minus I theta over 2i to prove this. It's easy. Sine of 2z is the same as 2 sine z cosine z. This is completely analogous to the real number which we expect them to be, right? So sine double angle formula. Sine of 2z equals 2 sine z cosine z. Well, that implies if I stay away from 0, right? If I stay away from 0, so first let's tackle the problem. Let's establish this for non-zero z. Let's start with that. The cosine of z must be sine of 2z over 2 sine z. right? Just take this expression, divide 2 sine z across. Well, using the infinite product representation, we now know how to write the sine of 2z. We know how to write the sine of z. Wait a minute, cosine z. Remember, again, I'm staying away from z equals 0. Sine of 2z over 2 sine z is 2z times, everywhere you see, z, just replace with 2z. On the top, you're going to get this product, right? Now, remember, it's z squared, but because you're plugging in 2z, so it's 2z quantity squared, so it becomes 4z squared, okay? But it's still over j squared pi squared, like this, the top. The bottom is 2 times sine z. What is sine z? Sine z is z times this infinite product, right? So 2z and 2z cancel. All I have left is just this infinite product divided by this infinite product. But now here's a trick. Look at the numerator, right? The numerator is 1 through j. J is 1, 2, 3, 4, and so on. What if I were to break it up? What if I were to take the odd indices first? So 1, the 3, the 5, the 7, and so on. And then I take up the even, the 2, the 4, the 6, and so on. Now you agree, I can do that, right? So in other words, I don't have to just multiply 1, 2, 3, 4 like that. I can do 1, 3, 5, 7, so on, all the odd, and then multiply 2, 4, 6, 8, all the even. It's the same thing. Well, at the top, if I'm only doing it odd, let's re-index. Let's call k, instead of j, use k. K equals 1 to infinity of 1 minus 4z squared over the quantity 2k minus 1 squared, pi squared. Because I'm only running odd, so this is equal to this. Now what happens in even? In even, let's use m. Right? Use m. Because I'm now doing even, so it's 2m quantity squared. Right? Everything else stays the same. M runs from 1 to infinity. So these are all the odd, these are all the even. The top. The bottom, instead of using j, let's go and use m because I want to show you that it will cancel. Let's just use m. So it's okay, right? I don't have to call it j. I can call it anything I want. I just call it m. I'm going to call m in the bottom. But now watch what happens. I can now regroup things a bit. This is just the first product, is the odd indices over here. And then over here, I got these two products. But wait, you look at these two products and you say, oh my God, they're exactly the same. Why is that? Because you see this 2m quantity square is the same as 4m squared. The 4 and the 4 cancel. All I have is c squared over, right, m squared pi squared. So the top is c squared over m squared pi squared. The bottom is c squared over m squared pi squared. This thing is 1. This thing just evaluates to 1. So all I have left is basically all the even indices just drop. It's just the odd indices. All right? And that establishes this expression. Okay, but wait a minute. Z is not equal to 0. What happened when z equals 0? Well, when z equals 0, it's okay. Because this product happens to just evaluate to 1 when z is 0. Again, go back here. Look at this product. What happens when you put in z equal to 0? Right? When z is equal to 0, this whole term here drops out. Because 4 times 0 squared is 0. So this is just 1. What is the infinite product of 1? 1. Right, so the infinite product of 1 is just 1. But that's exactly what cosine of 0 is supposed to be. If you go back to the definition of cosine, e to the iz plus e to the minus iz over 2. When z is 0, right, is e to the 0 plus e to the 0. But e to 0 is 1, so 1 plus 1 is 2. 2 over 2 is 1. So cosine of 0 is 1. So in other words, hey, even though I derive this without thinking z equals 0, but the end product actually is good for 0 as well. So in other words, for all complex z, cosine z is this infinite product. And that proves it. Okay, so this is the end of this a little bit longer video than usual. But again, so this establishes the product representation of sine cosine. Remember, you now know, again, if you don't, just go watch one of my 2 videos ago, I think. I established the series for sine and cosine, right? You can, even though we derive that with real argument, you can just easily plug in using the morph, right? You can clearly see that the complex version work exactly the same way. It's entirely analogous. And here we also now show you how to do a product representation of sine and cosine. So now you know sine and cosine in 2 different representation, and this sine and cosine, right, we can do it in a complex form. So again, I hope this is useful for you. Again, in the next few videos, I'm going to start looking at more we're going to start be using some of these. So again, in a lot of the applications, you will find that the product representation is actually far more useful than the series representation. Series representation have their use, of course, in a lot of applications, but the product representation, can be useful as well. And now you know how to do it. Again, well, I hope this is useful to you. Thank you for watching.